Hi, this series of videos is about learning C by example. That means with simple programs I will show you, for example, language features of this language. But the first few videos in the series is supposed to give you some helpful or in my opinion even necessary background in order to get actually started. You already know how to write this C code into some file. Use a compiler like GCC to translate it into an executable and then run this executable so that you actually see this message "Hello World" printed on the terminal. So you already probably have a clue what you would have to change in the C program so that it would print a different message. And from this starting point I could show you other features of C so that the program would print "Hello World" 10 times. Using a loop, for example, but that's not what this video is about. I will not show you these other language features. This will be the content of other videos, upcoming videos. This video is also not about explaining you in more details what this program actually contains. For example, the meanings of this hashtag include or this meaning of int main and open curly parentheses, that this is a function definition. This video is more about the question I asked myself after the Hello World program was explained to me as follows. The C code that you see is what a human can understand, and the compiler translates it into a machine code, into a code that only the computer understands. And this made me curious. I actually was more interested in understanding what is this machine code, this thing that a computer understands. And that's actually the topic of this video. To give you an idea what kind of things a computer understands. And this also is very helpful for two reasons. First of all, to understand what you can expect from the C programming language. What can be translated into something a computer understands. And second, in parallel to this videos about programming in C, we have these videos for building our own computer. So we should have an idea what our computer should be capable of, so that later we can use a C compiler to translate this C code into something our computer understands. So for us, a computer should not be just some black box. We should have at least some understanding about the components that are most relevant for programming, but also for building our own computer. We have to know what do we actually have to build so that you in the end have a computer that can be programmed and used just like the computer that you're currently sitting in front of. So what I will explain you are the components shown in this picture here. So you can think of this picture as a simplified version of a computer model, but actually I will explain you the components of the Ulm lecture machine. That's a computer that you're going to build. That mainly makes it easier for me to explain things because then I don't have to use phrases. This is almost like reality. It's almost like in an actual computer, because I'm talking about an actual computer. For you, a computer in the future, the computer that you are building. I will begin with the most important component for understanding C programming, the so-called memory. Think of the memory as an array of single memory cells. Each memory cell is a much smaller memory device where you only can store a few bits, a small piece of information. And these memory cells come one after each other. So in the picture below, for example, you see the first few memory cells of the memory. If I want to show you the complete memory, then I usually cannot display all the memory cells in one picture, but with a graphical notation like that, I can also say now you also see the last few memory cells. About the size of information that you can store in a memory cell. The unit for that is called a byte. In a memory cell, you always can store exactly 1 byte. But how many bits are actually available might be different from architecture to architecture. But if you want to make use of the C programming language, it's required that at least 8 bits are available. And to be historically correct, there used to be some computers where a byte consisted of, for example, 9 bits. But as I know of, there is no computer nowadays where it would be different from 8. And so also on the Ulm, on our computer, we will use exactly 8 bits for 1 byte. This also has the advantage that we can use exactly 2 hex digits for representing the content of a memory cell. And if it's clear from the context, like here, then I will also omit this prefix OX. The next thing you have to know about the memory is that each of this memory cell has an address. You can think of it as an index or a label or a name. So each memory cell can be referred by its address, and the first memory cell has the address 0. So this addressing or indexing begins at 0. And that means the next memory cell would have the address 1 and so on. So that means I can say, in this example, the memory cell with address 5 has the content hex 1F, like that. Now the last thing I want to talk about is the so-called address space. Think of it as the answer to the question, what would be the address of the last memory cell? But in order to talk about that, I also have to talk about the difference between a so-called physical and virtual memory. Obviously, the address space depends on how many memory cells are available, because the address of the last memory cell is the number of memory cells in total minus 1, because we begin counting with 0. Now, when you buy a computer, you buy together with some physical memory, and therefore the so-called physical address space basically depends on how much money you want to spend for a computer. Now for us, when we do programming, this physical address space is actually not of such a big relevance, because our programs either run on top of an operating system within some Unix process, or they run on the Ulm. And in both cases, we only access this physical memory indirectly through a so-called virtual memory. And this virtual memory can be much, much larger than the physical memory. For example, the Ulm provides a 64-bit virtual memory. That means you have 2 exponent 64 memory cells, and that means the address of the last memory cell would be 2 exponent 64 minus 1, or as I prefer to talk about that or to visualize it, the address of the first memory cell that is actually not available anymore would be 2 exponent 64. Now, such a 64-bit virtual memory is also typically supported by most operating systems nowadays. And if you use the right compiler flags, your program actually can take advantage of this virtual memory. Now, that means somehow the operating system or the Ulm have to take care of the fact that you might use in your virtual memory actually more memory than actually is available in physical form. But that's not a problem when we do the programming. That's a problem of the operating system, how to handle such cases, or the Ulm. So we will talk about that in another video. Before I continue, let me tell you why some people consider C as a low-level programming language, where you do programming close to the hardware. And that's because in other languages, like for example Java or Python, you don't have to know all these details about the memory, that it's organized in memory cells and that each memory cell has an address. The languages are basically hiding these details from you. In C, you need this detailed level of understanding. In C, you have to know that a variable, for example, is in general stored in memory, in one or more memory cells, coming one after each other, and that this variable has an address, the address of the first memory cell that is used. So now, why do we in this class consider C as a high-level programming language? Well, because we also do some programming in machine code or assembly code, which is equivalent to machine code. And then we also need a detailed understanding of all the other hardware components. In C, that's not required actually. C is supporting lots of different hardware architectures. That means you can write one C program and then compile it for different computers. And that means C is providing some level of abstraction to us. Now, that means that we don't have to know about the other components in such a detailed level, like the memory. But still, in my opinion, to understand any kind of abstraction, it's a good idea to begin with some special cases, so that we get an idea how, for example, these other components are working. And then later we can consider other special cases, and then we see what those cases have in common, and then we have an understanding of what these things are doing in principle. But that means on the following slides, I'm explicitly talking about features provided by the ULM. The CPU also contains some memory devices called CPU registers. Now, compared to the size of the virtual memory, the size of a single CPU register is first of all rather small. You only can store 64 bits or 8 bytes in one CPU register. And we only have a few of them. So CPU registers cannot be used for storing lots of data. But you can use them for doing certain operations. For example, you can store 2 integers in 2 registers, add these registers, and store the result in a 3rd register, something like that. So basically, I'm now starting to describe what kind of instructions are available on the ULM architecture. And that's describing, by example, one of these instruction kinds. Maybe you already now get an idea what other kind of instructions might be necessary. We will use the memory for storing data. And if we want to do computations on this data, we first have to copy this data from the memory into the CPU registers. And for that, the architecture provides some fetch instructions. And after such an operation was carried out, we probably want to copy the result back to memory. And for that, some store instructions are available. And also instructions for input and output can be actually be explained in this form. Think of an input instruction as reading from the input device one character somehow into a CPU register. So it's kind of a fetch instruction. And for printing some character, you basically can think of copying the content of a CPU register somehow to an output device. So this now describes 3 kinds of instructions very briefly. And I have to describe a 4th instruction kind in a bit more detail for explaining you how a program actually is represented and carried out. The last kind of instructions basically are so-called jump instructions. What all these instructions have in common is that we can use them for controlling the execution flow of a program. Now, in order to understand what it means to control the execution flow of a program, we first of all need some kind of understanding what it actually means to run a program, and that it actually happens in 2 steps, and each of these steps needs a bit of explanation. I mean, first of all, we have a executable in form of a file, somewhere written on the hard disk. And in order to execute it, it first needs to be loaded into memory. And there are a few details worth mentioning about that. And once this program is loaded into the memory contains somewhere a sequence of instructions. And running this program after it was loaded into memory means that these instructions then will be executed in a certain order. And also this is some concept that is worth to be explained in a bit more detail. When you use a C compiler to translate a C program into an executable, this executable will contain some bytes representing certain machine instructions. And it will also in general contain some bytes representing some data. Think of the Hello World program, then you need some bytes to describe this string that you want to print out. But it also will contain some additional information. Some information how to initialize the memory with these instructions and this data of this executable. And actually here we can be a bit more specific. This memory that is initialized, this memory cells, can be divided into different sections. You have some part of the memory that will be overwritten with the instructions, the so-called text segment. And after that, maybe after some gap, you have some block of memory that will be overwritten with the so-called initialized data. You will see these are basically global variables that you explicitly initialize with some non-zero value. And after that, you have a so-called BSS segment, which will be used for all the uninitialized global variables. And when you load the program, this BSS segment will be zero initialized with a 0-bit pattern. So after the program was loaded to memory, the text segment contains all these machine instructions from the executable. And in case of the Ulm, every machine instruction consists of exactly 4 bytes. And these instructions come one after each other without a gap in the text segment. Now, in order to understand the execution order, the sequential execution order of the program, you have to know 2 rules. Which instruction gets executed first, and in case of the Ulm, that's simply the first instruction of the text segment. So the address of the text segment specifies the so-called execution point of the program. And then secondly, you have to know what instruction gets executed next. And for most instructions, it's just the instruction that follows in memory. That's true for all the fetch instructions, store instructions, input-output instructions, or ALU instructions. And that means you have a typical control flow like that, where you just go from one instruction in memory to the next, except now this instruction is a so-called jump instruction, which in this case would jump back 4 instructions. So this is why jump instructions control the default flow of a program. And in this case, you also can visualize it with a flowchart like that. And maybe I also can mention here that these jump instructions actually come in 2 flavors. In this case, it represents, as you see from the flowchart, a so-called unconditional jump. And if that would be the only possible jump, then you only have programs that will run forever, because you always will jump, in this case, back. So you never can reach, for example, the last instruction that, in this case, hopefully will terminate the program. But we also have so-called conditional jumps. And in this case, if it's a conditional jump, you could visualize it in a flowchart like that, that depending on a certain condition, you either jump back or you continue with the instruction that comes next in memory. But this already might give you an idea that something like if statements, loops that you might have seen either already in C or other programming languages can be mapped to this kind of instructions that you see. And this mapping is actually done by the C compiler.